The last couple lessons, we've been talking about Einstein's theory of special relativity and how space and time are related. How if you move through space relative to an object, your perception of time for that object changes. And so this made physicists realize that space and time weren't completely separate things, that they were kind of connected to each other. And that's why they started referring to the two of them together as space-time. Well, it turns out that special relativity doesn't just draw connections between space and time. It draws connections between mass and energy as well, leading to the idea of something called mass energy, that these are not separate things, that they are connected. So to start this lesson, I want to just give you a bit of a visual that hopefully reviews some of the concepts we've talked about already and sort of introduces a new one. So I like to imagine you're watching a clock, and the clock is moving relative to you. As this clock moves, it was stationary and now it's moving. It's going faster and faster. 3 things will change as you watch it. The time between ticks gets longer. Remember we said moving clocks run slow from the perspective of an observer moving relative to it. So if time appears to be going slower, that means each tick takes longer. Now also, as this clock moves past you, its length gets shorter. Right? So these things are kind of doing opposites. The time between ticks is getting longer, but the length of the clock is getting shorter. And remember that length means something very specific here. It means the length that's parallel to the motion of the clock. So if the clock is sort of moving sideways across your field of view, the length really means sort of from the left side of the clock to the right side of the clock. That direction is parallel to the motion of the clock. The height of the clock, which we think of as sort of being up-down in this example, is perpendicular to the direction the clock's moving. So it does not change. It does not contract. He said it's only lengths parallel to the motion that are contracted. And the last thing that happens, so the time gets bigger, the length gets smaller, and its mass gets bigger. So 2 things that get bigger and 1 thing that gets smaller. Now remember, if you are moving with the clock, if you are holding this clock and you're the person running across the room with it, you will not notice any change to the clock's mass. You will not notice any change to the clock's length, and you will not notice any change to how long it takes the second hand to tick. These changes are only observed by someone who is not in the rest frame of the clock, someone who is moving relative to the clock. Okay, so focusing on this new one, this mass change, let's look at the formula we have for it. Note that mass increases, just like the time between ticks gets longer or increases. So both of these are governed by basically the exact same formula. So we're just, in effect, taking our time dilation formula, but replacing time with mass, which is going to look like this. The mass, as measured from someone moving relative to the object, is equal to the rest mass divided by square root of 1 minus v squared over c squared. So mr is the mass, it's called the rest mass. And it's measured, the mass that we would measure by someone in the rest frame of the clock, someone who does not see the clock as moving. And this m over here is my other mass. Mass measured from the other frame. The other frame being the one that sees the object as moving, the frame that is moving relative to the object. And again, with both of our other special relativity formulas, this is very forgiving with units. I can use any units I want for this speed as long as I use the same units for this speed. And I can use any units I want for this mass as long as I use the same units for this mass. Okay, now to kind of provide some motivation for what we're going to talk about next, I want you to put all this aside for now. Forget about special relativity. Forget about this course, and think about your previous physics course. Think about stuff that you thought was true in physics prior to studying special relativity. And I want you to try and think how you can figure out how much energy it takes to accelerate a 5 kilogram mass from rest to 100 million meters per second. So thinking about that, you might say, okay, well, 5 kilogram mass just sitting there at rest would have no energy. And if I want to get it going a high speed like this, I'm going to need to give it some energy. Specifically, I'm going to need to give it kinetic energy. So how much kinetic energy do I need to give it? Well, we have a formula for kinetic energy. So this is for a 5 kilogram mass. Formula for kinetic energy is 1/2 mv squared. So we say, well, the mass is 5 kilograms, and the speed I want to get it to is 1 times 10 to the 8, and that's going to be squared. So I get a kinetic energy of 2.50 times 10 to the 16 joules. That is a ton of energy. So that's how much kinetic energy this mass would have at the end once it has reached this speed. So that's the amount of energy I would have to give to it in order to get it to that speed. The second part of this question says, okay, how about if that was a 5.3 kilogram mass? Well, okay, let's do it again for a 5.3 kilogram mass. Seems kind of arbitrary why we're just decreasing the mass by this little amount, but let's do it. So the kinetic energy is still going to be 1/2 mv squared. Its mass is now 5.3, and the speed is the same. And I'm going to get 2.65 times 10 to the 16 joules. Okay, so if I want to get a 5 kilogram mass going this fast, I need to put this much energy into it. If I want to get the same speed for a 5.3 kilogram mass, I need to put this much energy in. The second amount being a little bit more than the first one. Okay, so why is this important? Well, the next question is, how about a mass that starts as a 5 kilogram mass and ends up as a 5.3 kilogram mass? Well, that seems a little random. But remember, as an object speeds up from our perspective, its mass increases. And indeed, if you took a 5 kilogram mass and brought it up to this speed, by the time you were there, it would no longer be a 5 kilogram mass. It would be a 5.3 kilogram mass, which is exactly why I chose that number. So what this means is that at the start, if you're taking this mass and you're accelerating it from rest up to that speed, at the beginning, you only have a 5 kilogram mass that you're pushing. So every little bit of effort you do produces a certain amount more kinetic energy. But as the mass goes faster and faster, it becomes harder and harder to accelerate it because the mass is getting heavier and heavier. And by the end, you've got a 5.3 kilogram mass, which is, noticeably a bit heavier. So it's becoming harder to accelerate it, harder to keep speeding it up than it was at the beginning. So if it stayed as 5 kilograms the whole time, this is how much energy would be required to speed it up. And if it started at 5.3 kilograms and stayed at that the whole time, this is how much energy would be required to speed it up. But since it starts as a 5 kilogram mass and ends up as a 5.3 kilogram mass, the amount of energy I'm actually going to have to put in is sort of somewhere between these two numbers. And it's not going to be just a nice average between them. It'll be somewhere between those two. So we need a way to be able to figure that out. We needed a way to talk about mass and energy in the context of special relativity. And this old formula, kinetic energy is 1/2 mv squared, is not going to work anymore because this formula assumes we know the mass of the object that is being sped up. And because our object's mass is now changing all the time, we can't simply put one number in for m. M would be a bunch of different numbers, and it's constantly changing. So this formula is no longer any good for us. If you find yourself using this formula in the context of a special relativity problem in this course, you're likely doing something wrong. So let's figure out what we can do to solve problems like this. And the point I'm kind of getting at is this. Working with energy is hard when we consider special relativity because energy depends on mass. And mass increases with speed. Most of the energy formulas you can think of have mass in them. Kinetic energy, the one we looked at, is 1/2 mv squared. The formula for gravitational potential energy is mgh. The formula for heat, which is the transfer of thermal energy, is mc delta T. So energy is sort of inextricably linked with mass. And if mass is going to be always changing on us as things speed up in special relativity, that's going to throw off our traditional energy equations. Thankfully, there was this nifty guy called Einstein who came up with a formula to help us work with mass and energy in the context of special relativity. And that formula he came up with for us, which you may have heard of before, is E equals mc squared. Okay, well, c we know is the speed of light, 3 times 10 to the 8 meters per second. M is the mass of an object. In kilograms. And E is the energy of an object. In joules. Now, a note I'm going to add here is that there's sort of two different types of mass and energy that this equation works with. How do I explain this? You are used to objects that are just sitting there, not doing anything, not being lifted, not being heated, not being thrown. Objects just sitting there. You're used to them having mass. But what this formula tells us is that whenever we have mass, we have energy. So now, those objects that are just sitting there, that are stationary, that are at rest, not only do we have to think of them as having mass, we also have to think of them as having energy. And that energy is called rest energy. You can think of rest energy as this. So if you go way back to the time of the Big Bang, when the universe was created, shortly after the Big Bang, all the universe had in it was energy. There was no matter. There were no electrons, there were no protons, no atoms, no galaxies, no stars, no planets, just pure energy. And a little while later, some of that energy started getting converted into matter, into electrons, and things like that. So, all the matter that's in the universe today, all the galaxies, all the suns, all the stars, all the planets, all the gases, all the protons and neutrons and electrons, all of those were created from pure energy shortly after the time of the Big Bang. So, in a sense, every piece of matter kind of has stored in it that energy that was used to create it. This is called rest energy. It's the energy that you will always have in an object, even when it's completely at rest, when it hasn't been lifted and given any potential energy, when it hasn't been heated and given any thermal energy, when all the conventional forms of energy that we think about are absent from an object. As long as it is still an object, as long as it's still a piece of matter, it will still have its rest energy. I like to call this the energy of existence. So, an object at rest, we always know it has mass, and now we know it has what's called rest energy as well. When I speed an object up, we know that it gains energy. It gains some kinetic energy. And this formula tells us that when it gains energy, it's going to have to gain mass as well. And that jibes with what we said on the previous page here about mass increasing as an object speeds up. So this formula is actually quite versatile. We can use it for objects at rest, where this is the rest mass and this is the rest energy. And we can use it for objects that have started moving, where this is the new increased mass and this is the new increased energy from the added kinetic energy that comes from motion. So let's just add a note about that here. Okay, so just like space and time are connected, which led us to this word space-time, mass and energy are also connected, which leads to us referring to them as mass energy. In high school, in your physics class, you probably talk about the law of conservation of energy. And in your chemistry class, you probably talk about the law of conservation of mass. But if you get to a high enough level in physics at university and you study these things, they stop talking about conservation of mass and conservation of energy as if they're separate things, and they talk about the conservation of mass energy. If one's conserved, then the other has to be too. Because it turns out mass and energy aren't just connected, they're the same thing. what I mean by this is if you know one, you can immediately calculate the other. You don't need to know anything else. So they're not the same thing in that they'll be the same numbers, right? One is measured in kilograms and one is measured in joules. But it's sort of like saying feet and meters are the same thing. Yeah, they're different units. And if I measure something in feet and I measure something in meters, I get different numbers. But they're really measuring the same thing. They're measuring length. And if I know the length of something in feet, I can basically immediately know it in meters. I just have to do a quick conversion. It's the same with mass and energy. If I know an object's mass, I can right away quickly convert it to find the object's energy by using E equals mc squared. So I like to think of mass and energy rather than being different things. I like to think of them as just different units for the same thing. Just like feet and meters are different units for measuring length. So with this in mind, let's try a little problem. Calculate the mass and energy of a 5 kilogram object at rest and after 10 to the 17 joules of work have been done to speed it up. So here we are looking at, this is sort of a common problem where I'm interested in mass and energy, and I'm interested in an object that's, at rest in one sense and sped up in another sense. There's sort of like 4 things I'm interested in: mass, energy, at rest, and sped up. And I find it useful to attack problems like this with a bit of a chart. So there is the mass I'm interested in, and there's the energy I'm interested in. And I'm interested in these both before it's been sped up and after it's been sped up. Okay. So, there are a couple of equations we can use from today's lesson that'll help with this. So we said above here that when it comes to mass and energy, basically if I know one of them, I can find the other right away from this equation. So if I'm talking about before the object has been sped up, if I know one of these two things, the mass or the energy, I can right away find the other by using E equals mc squared. So that equation is like a bridge that helps me get back and forth between mass and energy, in this case before the object has been sped up. And like I said up here, this equation works whether I'm talking about rest mass and rest energy or total mass and total energy. So I can use it before my object has been sped up, when we're talking about rest mass and rest energy, or I can use it after my object has been sped up, in which case we'll be talking about total mass, the rest mass, plus the new mass it got from speeding up, and the total energy, the rest energy plus the new kinetic energy it got from speeding up. So E equals mc squared works down here as well, to go back and forth between those two. Now, I also would be nice if I could kind of go between rows of this chart. If I could kind of go this way between mass and mass, or this way between energy and energy, and indeed we can. This formula we got earlier in this lesson shows me how to go between the rest mass and the mass once the object is moving. So that equation I can use down here to go between these two masses. Okay. And then finally on this side, how do I get back and forth between the energy it had before it started moving and the energy it has after it started moving? Well, the difference between those two is just the change in energy, the new kinetic energy that's added. So there's no real fancy formula here. We just have to look at the change in energy. And there's no formula for that. So let's look at this particular problem now. I have an object that is 5 kilograms at rest. So that'll be my mass before I've started to speed it up. Let's add that in. Mass before I sped it up is 5 kilograms. And I know we're going to do 10 to the 17 joules of work on it. Well, right away, remember we said since mass and energy are basically the same thing, as soon as I know one, I can quickly convert and find the other using E equals mc squared. So let's do that right now. To find the energy over here, I'm going to say E equals mc squared. The mass is 5. C is 3 times 10 to the 8. And I square it. And that's going to give me 4.50 times 10 to the 17 joules. Let's stop and think about this for a second. This is a huge amount of energy. Usually in physics, when we talk about, objects speeding up, getting kinetic energy, or going up a hill and getting potential energy, we're talking like joules, or like hundreds of joules, or thousands of joules. But like 10 to the 17 joules, that is phenomenally large. And that's this type of energy that we were never even talking about before. We were making a big deal about, a couple joules here from gaining some height and a few joules over here from gaining some speed. Meanwhile, all of these objects had like 10 to the 17 joules of energy just sitting in them from existing. So the amount of energy it took to create the matter that is in an object which is this sort of number here, is way bigger than any amount of energy you could possibly imagine to give that object by speeding it up or lifting it up a hill or something like that. And it's just been kind of there in the background the whole time, rest energy. All right, so now let's see if we can figure out some of the other sections of this table. Well, the question tells us that I'm doing 10 to the 17 joules of work when I speed it up. Now remember, work is just energy being transferred from one object to another or from one form to another. And indeed, when I speed up an object, I'm going to have to transfer some energy to it because I have to somehow give it some kinetic energy. So this 10 to the 17 joules basically tells us how much energy is going to be added. It tells us the change in energy for this object. This is the energy that is being added to it in order to speed it up. So my new energy, after it's sped up, is going to be my old energy, 4.50 times 10 to the 17 joules, plus the new energy I've added, which is 10 to the 17 joules. And 4.5 times 10 to the 17 plus 10 to the 17 is 5.5 times 10 to the 17 joules. Okay. So this is how much mass my object has when it's just sitting there. And because mass and energy are the same thing, this is how much energy it has when it's just sitting there. We call this the rest energy. Then if I speed it up, I'm going to give it some kinetic energy. That was this amount here. And so its new total energy is now this number, the rest energy plus the kinetic energy I just gave it. And because the energy went up, that means the mass had to go up too. But I can find its new mass by just using E equals mc squared. Remember, if I know the energy, I can just use that to convert to the mass, because they are the same thing. So E equals mc squared. Here I want to find the mass, so if I rearrange this to isolate m, I have E over c squared. My energy is 5.5 times 10 to the 17 joules. C is 3 times 10 to the 8. And I get a new mass of 6.11 kilograms. So all this energy I added, 10 to the 17 joules, which is a ton, only gave me like an extra kilogram in mass. That gives you a sense of how much energy is in just a little bit of matter. Now, just for general interest, this rest energy that's sort of in an object all the time, I've called it the energy of existence or the energy of creation, the energy that was used shortly after the Big Bang to create all the atoms that are in that object. It's huge compared to all the traditional types of energy we've talked about. And if you could find some way to get that energy out, to convert that matter back into pure energy, that would either make a tremendous weapon or an infinite supply of power for the human race. Now, the universe does allow for matter to be converted back into pure energy, sort of the opposite of what happened shortly after the Big Bang. And that did actually happen quite a bit after the Big Bang. Energy would be converted into matter, and it turns out it was also converted into antimatter at the same time. And if a piece of matter and antimatter that matched up found each other, they would actually annihilate and turn back into pure energy. So it was really hard for the universe at the beginning to make matter and have it stay, because the universe had to make matter and antimatter in equal parts, and then they would keep finding each other and getting converted back into pure energy. But for reasons we don't really understand, we think the universe ended up making a little bit more matter than antimatter. So after all the antimatter had sort of like canceled out and been annihilated by finding bits of matter, there was a little tiny bit of regular matter left over. And that little tiny bit of leftover matter is all the matter that's currently in the universe today. All the suns, all the galaxies, all the stars, all the planets, everything. Now, I guess it's possible there's still a little bit of antimatter kicking around out there. And if you came across some and brought it in contact with its matching matter, then the two would annihilate each other and turn back into pure energy. And the rest energy of that object would be sort of realized again and not stored in the object. But without having access to antimatter, it's pretty tough to do this. So the rest energy that an object has is likely to just stay with that object forever. Okay, so quick recap here. If you're moving with an object and you travel with it, you're in its rest frame, you never notice time to travel at any different speed, you never notice lengths to get changed, you never notice its mass to change. But if an object is moving relative to you, then times you observe for that object are longer. The length of that object is shorter, but its height isn't. And the mass of that object is bigger. And we can use this formula here to find out just how much bigger the mass gets. When we want to talk about mass and energy and how they affect each other, we need to use this equation, E equals mc squared, if we're talking about things moving, close to the speed of light. And the big take home here is that mass and energy are the same thing. One's measured in kilograms, one's measured in joules, but we're basically just doing a unit conversion. To turn mass into energy, I just multiply it by this one number. And to go the other way around, I'm dividing. So that means anytime I have mass, I have energy, and anytime I have energy, I have mass. So if I have an object just sitting there on the table, well, we know it has mass. That means it must have energy as well, which I can calculate using this. And if I speed an object up, we know that I'm giving it a little bit of extra energy. And that means I must be giving it a little bit of extra mass as well. And again, E equals mc squared helps me kind of connect those two. All right. Hopefully this lesson has helped you to understand a little bit what happens to objects when they speed up from the perspective of an observer, and how mass and energy are really, really closely connected to each other, and how it's hard to talk about one without the other when we're talking about situations in special relativity.